Welcome back to Labyrinth Academy. I'm Madhulya Narachi, your physics tutor. Today we are starting into physics, unit 6C.1, magnetic fields. You have all seen magnet sticks to fridge or track paper clips, but in this lesson we'll go beyond the everyday observation. We'll learn what a magnetic field really is, how to measure its strength using plus and plus density, and how coils of wire allow us to link magnetic fields with electricity. Let's get started. When we see a magnet move towards the fridge, it looks like the magnet is simply moving on its own. But Newton's third law tells us that forces come in pairs. The magnet pulls on the fridge and the fridge pulls equally on the magnet. Newton's second law explains the difference in motion. Acceleration depends on both force and mass, so the fridge barely moves because it's massive, while the lighter magnet accelerates quickly and sticks. This simple example shows how Newton's laws describe motion caused by forces. Newton explains how objects respond to forces, but where do the forces come from? That's where fields come in. Electric and magnetic forces are part of the same phenomenon called electromagnetism. Moving charges create magnetic fields, and changing magnetic fields create electric fields. Together, they explain light, radio waves, and all forms of electromagnetic radiation. An electric field is a region where a charged particle feels a force. Similarly, a magnetic field is a region where a magnetic pole experiences a force. In the bridge magnet example, the magnet is inside the fridge magnetic field, which is why it experiences a pull. The field lines we draw indicate the direction of a north pole would be pushed. Magnetic poles always come in north-south pairs. Just like electric fields, magnetic fields are stronger where the lines are closer together. At the ends of a bar magnet, the field lines are densest. That's why a paperclip will jump onto the end of a magnet. The magnetic force is strongest there. Magnetic plus phi measures the total magnetic field passing through a certain area. We calculate it by multiplying the magnetic plus density B, the area A, and the sine of the angle between the field and the area. This tells us how much of the field is linking with that surface. If the magnetic field is perpendicular to the area, the angle is 90 degrees. In that case, sine theta equals 1. So the plus phi simplifies to b times a. This makes calculations simpler when the field is perpendicular to the surface. We call B the magnetic plus density or magnetic field strength. Dividing plus by area shows how dense the field lines are. The denser the lines, the stronger the field. That's why B is also known as magnetic field strength. Its SI unit is a Tesla. In practical applications, a single wire experiences too small an effect from a magnetic field. That's why we use coils of wire. Each turn interacts with the magnetic field, so the effect is multiplied by the number of turns in. This product of plus and number of turns is called plus linkage, measured in Weber turns. So plus linkage equals B times A times N. So to conclude, a magnetic field is a region where poles feel a force. Its strength is measured using plus density B. The total field passing through an area is plus pi, and in coils we describe the effect with plus linkage n pi. These concepts form the bridge between magnetism and electricity. That's all for today's lesson. In the next video, we'll explore the electric motors. If you find this lesson helpful, don't forget to like the video, subscribe to Labyrinth Academy, and check out other lessons and our educational documentaries. See you next time.